Welcome to CLE 204 Construction Materials and Technology, and this is Unit 1 Sources of Aggregates and its Properties. Let's get started. Here is the content of Unit 1. Initially, we deal with the physical and mechanical properties of construction materials, and later in the study, we'll focus the construction materials such as stones, aggregates, and bricks in detail. Finally, we do an introspective assessment of various testing procedures adapted for these construction materials, and these things are based on BIS, that is Bureau of Indian Standard. In this short video, we focuses primarily on the physical properties of construction materials. Let's define what is physical properties. Any property that is measurable and which doesn't alter its characteristics, that is a physical state of the material, is commonly known as physical properties. The examples of physical properties are specific mass, also known as density, and specific gravity, also known as relative density, and specific weight, known as unit weight, porosity, and so on. And in the subsequent sections, we'll deal with the physical properties. Some of the important physical properties such as density and specific gravity and so on. First is density. What is density? Density is the ratio of mass per unit volume of a homogeneous material. And this is also known as volumetric mass density or specific mass. It is denoted by a Greek letter rho. Mathematically, density can be written as m over v. M is mass of the material in terms of kilogram, or V is the volume of the material in terms of meter cube. And there is another type of density known as weight density, which is nothing but ratio of weight per unit volume of a material. Weight can be expressed as mass times the gravity, that is acceleration due to gravity. And when you substitute m over v in terms of rho, weight density can also written as weight density is equal to rho times the g. G is acceleration due to gravity, and it expressed in meter per second square. Generally, G is 9.81 meter per second square on Earth. The unit of density is kilogram per meter cube, and also the unit of weight density is also expressed in kilogram per meter cube. Some of the commonly used construction or building materials and its associated density values are given in the next diagram. And these are the commonly used construction materials and its associated density values. Note down that steel has a higher density value, which is 7,833 kilogram per meter cube, whereas water has a density range of 1,000 kilogram per meter cube, and some of the material which has lesser density known as polystyrene foam, and which has only just 33 kilogram per meter cube. And these are some of the examples of construction materials and its density values. The next most important property is the bulk density, denoted by the Greek letter rho and the underscore p, which denotes bulk density, which is the ratio of mass per unit volume of a material in its natural state. Note on that the natural state denotes a material with its eccentric voids and pores. The intrinsic characteristics or intrinsic voids or pores are generally not considered because of its you know uh, huge nature, or doesn't makes much difference in the terms of calculations. For example, a fire clay bricks generally consider a macroscopic pores rather than the intrinsic mesoscopic pores, which is the inherent characteristics of a brittle materials. The bulk density mathematically represented similarly to a density, which is m over v, that is mass of the material divided by the volume of the material. And the unit of bulk density is also kilogram per meter cube. Bulk density can be classified into two, such as wet bulk density and dry bulk density. Dry bulk density is also the bulk density, and wet bulk density has a little difference. The difference is that it considers the amount of moisture or the water present in the materials. And bulk density are generally the properties of the granular materials. That is, it is commonly also known as density of granular materials. Wet bulk density is the ratio of total mass of the material, that is the mass of material plus the mass of the water, as I told you, and to the volume of the total material, which is the volume of the material plus the volume of the water. And dry bulk density is also known as bulk density, which is mass over volume, whereas wet bulk density has a little difference, that is the total mass divided by the total volume of the material. The total volume considers the total volume of material plus the volume of the water, and mass also, mass of the material plus mass of the water. And it's also represented in kilogram per meter cube. Let's do a problem. Calculate the bulk density of a brick, and this is typically a brick which has the dimension of 9 centimeter height, 9 centimeter breadth, and length of 19 centimeters. A standard brick which has a frog. Frog is an indentation at the top which has the length of 10 centimeters and width of 4 centimeters and a height or depth of 2 centimeters. And take down this problem. As I read, take down this problem. Calculate the dry and bulk density of the structural fire clay bricks of standard dimension, which is 19 by 9 by 9 centimeters, with the standard frog size of 10 by 4 by 2 centimeters, as shown below. The weight of the brick, which is dried naturally at 27 plus 1 plus or minus 1 degree Celsius temperature, which is standard room temperature, is 2.76 kilogram. And the weight of the brick removed after the immersed and soaked in cold water for 24 hours is found to be 3.12 kilogram, and this is based on BIS, that's Bureau of Indian Standard Testing Procedures. The volume of the water consumed by the brick is found to be 0.0009 meter cube. Now it's our time to find out the bulk density of this material in terms of dry bulk density and wet bulk density. And now let's calculate the bulk density of this brick. Let's take down the given data. That's the data is given in the problem. The dimension of the brick, which is the standard dimension, which is length into B into D, which is 19 by 9 by 9 centimeters, which comes around volume is calculated based on length into B into D, which is 0.001539 meter cube. I recommend you to take everything in terms of meter cube. Do not convert this in centimeters or any other units. That will become a difficulty in terms of the final calculation. And the dimension of the frog is the small l, b, and d, which is nothing but the standard dimension of the frogs. And when you have that dimension, you can calculate the volume of the frog. The actual volume of the brick in the dry state is the total volume of the brick minus the volume of the frog. Frog is actually an indentation, and we need to remove that because it will create an error in terms of final calculation. And if you see that, the total brick and this indentation or the voids or the gap, and this is generally removed from the original dimensioning of the brick, and that will give you the total volume of the brick in dry state. And mass of the brick, we know that initial mass is 2.76 from this calculation. And finally, the total mass of the brick after it gets soaked in water, like after the testing procedure, it is just 3.12 kilogram. It's the final mass. This consists total mass of the brick plus the mass of the water. And the mass of water generally calculated based on the reverse iteration. That is, this has total mass of the materials, that is mass of the material plus the mass of the water. And if you want to find a mass of the water, we need to find the total mass of the brick, that is empty, this value, minus the total initial mass of the brick. That will give you the mass of the water. Similarly, the volume of the water is obtained from the given data, and the volume of the brick in the wet state is found out using the volume of the brick at a dry state plus the volume of water. We also know that volume of the brick in the dry state is 0.001539 meter cube, and in the wet state it is given from the question, that's 0.009 meter cube. And totally we have 0.0024 meter cube. This is the total volume of the brick in wet condition. Once you have formulated all those things, and putting in an equation is not a very big deal. And the next is the bulk density calculation. Dry bulk density and wet bulk density, as we know, that is represented as mass over volume, and for wet bulk density it is total mass divided by total volume. Dry bulk density is the mass over volume. This is the initial mass 2.76 divided by the volume of the brick in the dry state, which is 1840 kilogram per meter cube. Whereas in the wet bulk density, it is the total mass of the material, that is mass of material plus mass of water, which is 3.12, and total volume of the material, that is the mass of material plus volume of material plus the volume of the water, which is a 0.0024, which comes under 1300 kilogram per meter cube. and this concludes the problem. Another important property is the density index. Once we study density and bulk density, and this is an inherent property, that is the amount of homogeneity a material can hold. Density index is represented by rho, subscript of O. It is defined as the ratio of bulk density to the density of the same material. Mathematically, it is bulk density divided by the density, which is rho B divided by rho. And density index is a constant. In generally, the density index of most of the building and construction materials are less than or nearly equal 1, but they are never exactly equal 1. This is a reason, like bulk density and density cannot have a same value, as bulk density has inherent properties of considering voids and other elements, so which will not match with the density, or in natural state no material exists perfect ideal or something like that. So that's the reason density index of construction materials never be equal 1. Remember this point. Density index of any construction material never be equal to 1, but it can be nearly equal to 1, like 0.98, 94, 96, and so on. Let's do a problem. Calculate the density index of a structural fire clad bricks whose density and bulk densities are given as 1971 kg per meter cube and 1840 kg per meter cube respectively. And the rho was given, and rho B is also given. Density index is nothing but the division of rho B over rho, which is bulk density divided by the density, which is 0.93353, approximately it's 0.94, which is a constant, and hence the density index of the structural fire clad brick is 0.94, and it is less than 1. And this concludes the problem. The other most important physical properties of construction materials is the unit weight or specific weight. This we have already dealt in the density, which is the weight density, that is rho W, which is nothing but the weight divided by the volume. Weight is nothing but the mass into acceleration due to gravity and divided by volume. And this is represented by a Greek letter gamma. As I told you that m over v is rho. When you substitute rho in this equation, we will get this gamma is equal to rho times the g, acceleration due to gravity, and this is unit weight. It plays a key role in terms of structural engineering calculation, or the design load calculations. Like for example, it plays a key role in structural engineering, like determination of load and along with the angle of internal frictions. A comprehensive list of weight and weight densities and other unit weights of materials, commonly used building materials, can be found in IS 875 Part 1 1987, which is the code of practice for design loads other than earthquake for building and structures, Part 1, that is dead load, unit weights of building materials and stored materials. You can navigate to this link and download the full documents of IS 875 Part 1 for free. And let's do a problem. The unit weight of hardened plain cement concrete is to be calculated, whose density is given as 2400 kilogram per meter cube. Remember the table we discussed during the density, the list of items and its corresponding density values, and concrete has a density of 2400 kilogram per meter cube. And we need to find out the unit weight of plain cement concrete, and we use this relation. Question number 6. When we know rho in G, we can find out the unit weight. Rho is the density. In this example, it is 2400, and G is 9.81, and we can find out the unit weight. And thus the value 23544 Newton per meter cube. We can convert that into kilonewton per meter cube, so multiplying by 10 power minus 3. 10 power minus 3 will take you decimal value here and will become a kilonewton per meter cube, and this is approximated to be 24 kilonewton per meter cube. This is the most important thing which we require during the design calculations. If you calculate the slab unit weight or anything which considers concrete, and this is the unit weight of concrete, plain cement concrete. There's a slight difference in terms of reinforced concrete, that is adding rebar to a concrete, whereas the unit weight of rebar attached concrete or reinforced concrete is generally is 25 kilonewton per meter cube. Remember that in mind. And here is the unit weight of some of the commonly used construction and building materials. And to be note that like this is very similar to the graph which we showed in our density. For example, the density of water is 1000, whereas in the unit weight of water is just 9.8 kilonewton per meter cube. It's all very similar to what we dealt in the density of these construction materials. And the concrete has the density around 2400, and this has around 24 kilonewton per meter cube as a unit weight. The next is specific gravity, which is also considered as important physical properties of building materials, which is the ratio of unit weight of materials divided by the unit weight of the reference materials. The reference materials are the material which has the defined or the proper unit weight. Like for example, it just is considered a material over in a specific reference material. For example, the unit weight of water is just 9.8 kilonewton per meter cube. Any material which is measured over 9.8 kilonewton will give you the specific gravity. And unit weight is nothing but the rho into the gravity, that's acceleration due to gravity, and this is the ratio of unit weights, and the g gets cancelled so as to give the unit density of materials divided by the density of water, and hence this is also known as relative density, that is the density of materials over the density of water. Water has a density of 1000 kilogram meter cube at 4 degrees Celsius, and to define it precisely, it is the ratio of mass or weight of a volume, that is density or unit weight of the material, to the mass or weight of a volume, or that is density or unit weight of the reference material, and that is called specific gravity. And the specific gravity has two components. One is called apparent specific gravity, and next is called absolute specific gravity. Apparent specific gravity is the one which considers both intrinsic and extrinsic voids in the natural state. That is, the inherent voids and exherent characteristics like the brittle fractures and all considered. That type of specific gravity calculation is called apparent specific gravity. And this is also known as mass specific gravity. There is another type of specific gravity known as absolute specific gravity, which doesn't consider the intrinsic voids, that is, just excluding voids in a volume. So this is kind of absolute specific gravity, and this is known as true specific gravity. It doesn't consider the voids in a volume of a sample. And two components, one is called apparent specific gravity and absolute specific gravity. Let's do a problem. Calculation of apparent specific and absolute specific gravity. For example, let us consider mineral admixture used for concrete, whose natural state density will be around 1442 kilogram per meter cube, and whose compacted density, like when densified or compacted in terms of air removed or any other process, and this is 1922 kilogram per meter cube respectively. From this equation we know that the specific gravity is just the ratio of gamma m, unit weight of materials, divided by gamma of water, or it can be represented as the density of materials over the density of water. And in this particular example, we have two density values given. One is the natural state and the loose state, and another one is the compacted state. And this is called undensified value, and this is called undensified this unit, right? I'm sorry, densified specific densified density. Okay, so undensified value of density of this mineral sample is given as 1442 kilogram per meter cube, and densified value is 1922 kilogram per meter cube. And we also know that the reference material, which is the density of water, which has a density of 1000 kilogram per meter cube. Apparent specific gravity is just taken as undensified value, which is like inherent voids in the air present in the material sample, which is this value 1442 divided by 1000, which is 1.442, which is a constant. But absolute specific gravity is a true specific gravity, which is considered as 1922 divided by 1000, so 1.922. It's also a constant. And this the characteristics of absolute specific gravity and apparent specific gravity. And here is a list of specific gravities of different construction building materials. And note that the specific gravity of water is 1, and hence it is used as a reference material. And now you understand the reason behind this, behind the usage of water as the reference materials. The next is very important concept called relative volume fraction. Three important concepts: one is called porosity, compactness, and volume ratio. Porosity is nothing but the ratio of volume of voids of a material to the apparent volume of the material. That is, air present in a material divided by the total volume of the, or the apparent volume of the materials. Apparent specific gravity is just considering the external voids. So that's the idea. So apparent volume of material just considering everything, the voids and all, something like that. So volume of voids divided by the volume of materials will give you the porosity, the amount of pores present in the materials. Mathematically, porosity is denoted by small letter p is equal to volume of voids, that's V subscript E, divided by the apparent volume is a capital V. Apparent volume just considering voids as well as the volume of the material, that is given as volume of materials and plus the volume of voids or the air present in it. And the another concept is called compactness, which is denoted by small letter C, is the ratio of volume of the materials divided by the apparent volume. Volume of the material, just like in porosity, we consider the volume of voids divided by the apparent, and here it is volume of materials divided by the apparent volume. To be note that we can represent it C and P in terms of a single equations. For that, take this equation: C is equal to Vm divided by capital V, which is Vm is also known as the volume, total volume minus the volume of voids. And when you divide it over capital V, we'll get this form of equation. There is 1 minus voids divided by the volume of apparent volume of the materials. We also know that apparent volume of voids divided by the apparent volume of materials is small p. We can substitute p in terms of V divided by V. So this equation becomes 1 minus p, and hence C is equal to 1 minus p. The next is very important, called void ratio. Void ratio is the important factor that we'll consider in soil mechanics and other related stuff, and it is denoted by small letter e, which is the ratio of voids divided by the volume of the material, that is including the volume of voids, that's the volume of the materials. So we also can represent C and P in terms of V. So take down the equation: V suffix E divided by V suffix M is equal to Vm. We know that it is excluding the voids. So apparent volume minus excluding minus the voids will give you the Vm. So we have this formulation, and we take E outside. So this becomes this, like V minus E. When you take VE outside, small ve, so this gets divided by ve, and ve divided by ve, it's equal to 1. So we have ve outside, and this gets cancels each other. For example, this gets cancelled each other and then becomes 1. And we also know that volume of voids divided by the volume apparent volume is porosity. So this is kind of an inverse. So apparent volume divided by the volume of voids is just nothing but the 1 divided by P, that is porosity. So we have this form, and P gets numerator, and P divided by 1 minus P, and eventually we also have found out in the previous equation that 1 minus P is nothing but the compactness C. So 1 minus P is nothing but C. So substitute 1 C in place of 1 minus P, and we have E is equal to P by C. And this relates all the three things: porosity, compactness, and void ratio. And you can also represent in a different way, that P is equal to E by C and P into C, and so on. So knowing one quantity, we can enable to find out the other two quantities easily just by the calculations. And these things are very important: porosity, compactness, and void ratios are three quantities that characteristics the relative volume fraction of voids and materials. And this concludes this short lecture, and the next lecture will focuses on mechanical properties of building and construction materials. Thank you for watching this short introduction to the construction materials and technology. I hope we will upload many more videos in near future. For the original content of this lecture can be downloaded from the slideshare.net. The URL is given below. Thank you.